Hello physicists, welcome back to another video. Today we're going to be talking about a new branch of physics called kinematics. And when I say new, I mean new for us. It's actually a very old branch of physics and it dates back way before our time. So today we're going to be talking about kinematics, which is a study of physics that doesn't involve forces. We're going to be describing the motion of objects without forces. We will get to forces later in the year with Newton's laws and such, but for now, we're going to be operating without forces. We're going to be talking about the motion of objects with things like position. We're going to be using position. We're going to be using velocity, and we're going to be using acceleration. Okay, those are our three big ways of describing motion. And kinematics only really applies if we have a constant acceleration, okay? Or at least kinematics with just algebra. If we have a constant acceleration, then we are able to use kinematics. So for this unit, we're going to be describing the motion of objects that have a constant acceleration. Sometimes people call kinematics the geometry of motion because it's very geometric in its nature. We're going to be using a lot of triangles, and the whole reason that we covered trigonometry is for this unit, as the basis for this unit. We will look at it again in forces too, but kinematics has a huge part of it that is connected with geometry. And we're going to be calculating trajectories and using it to calculate the trajectories of projectiles. That's one of the biggest aspects of kinematics. Really, the summation of kinematics, in my opinion, is projectile motion, and talking about the trajectories that projectiles take when they fly through the air. And we'll get to some fun stuff later on when we start launching projectiles and talking about their trajectories. But for now, we're going to stick with a little bit of a simpler version of kinematics and build our way up to that projectile motion. Okay? So, before we begin with kinematics, we first need to define two very important concepts for kinematics and for physics in general. We need to talk about scalars and vectors. Scalars and vectors are two different types of quantities. These are categories, okay? And many of the things that we talk about, like position and time and acceleration and velocity, fit under one of these two categories, scalar or vector. And the difference between a scalar and a vector is that a scalar has magnitude, okay? Scalar has magnitude, which is just some quantity. So when we talk about length, we could say something is 30 meters. We could say something is 50 meters. We could say something is 2 meters. That number, that 2, that 30, that 50, that is our magnitude. And so these are all examples of scalars. They're just a magnitude, okay? And they can have some unit associated with them, like meters, but we're just talking about some magnitude. Meanwhile, vectors have magnitude, so they have some quantity associated with them, some number, but they also have a second component to them that scalars don't have. They have direction, okay? If you're familiar with the movie Despicable Me, you remember that the villain of Despicable Me was known as Vector, and he has a line in the movie where he says, I have magnitude and direction or something like that, blah, blah, blah. That comes from physics, actually. And so magnitude and direction are the two components of a vector. So an example of a vector would be 20 meters east, okay? So we have our magnitude here. We have our magnitude, which is our number, which is 20. Then we have our unit, which we're always going to have. And then we have our direction, which is east, okay? So now let's take a look at some examples of some quantities and see if we can categorize them as a scalar or a vector. So over here on the left-hand side, I have 5 little quantities. I have 1 light year, 12 meters per second southeast, blah, blah, blah. And we're going to decide whether they're a scalar or a vector. So 1 light year, is this a scalar or a vector? Well, our way of deciding is, does it have a direction or not? If it does have a direction, it's a vector. And if it doesn't, it's a scalar. So pause the video for a second, see what you think it is. And okay, 1 light year has no direction associated with it, so this is going to be a scalar. Okay? Now the next one, 12 meters per second southeast. Take a second to pause the video, see if you can decide which one it is. And if you said it was a vector, you would be right because southeast is a direction. Okay? Southeast is a direction. Now let's do the next one, 14 meters at 30 degrees. This one seems a little tricky, but pause the video. And if you said this one was also a vector, you would be correct. And how is 30 degrees a direction? Well, let's take a look. Okay, let's draw a little XY grid up in this left-hand corner. The direction 30 degrees, if it doesn't say 30 degrees from north or 30 degrees from west, then we assume that it's from the positive X direction, so from the eastward direction, okay? And going 30 degrees from east might look something like this. It's more like 45, that was bad. This is more like 30, okay? So pointing at an angle of 30 degrees up, or the video's reversed, pointing at an angle of 30 degrees up is what we mean by at 30 degrees, okay? So that would be our direction associated with it. And all right, let's do the next one. This next one is 25 kilograms, scalar or vector. Take a moment to pause the video. And if you said this was a scalar, you are correct. It does not have a direction associated with it. All it has is a unit, kilograms. That unit's always going to be there for a scalar or a vector. Remember, the direction is what separates them. And finally, 10 newtons to the left. Take a moment to pause. And if you said it was a vector, you were correct because to the left is a direction. And oftentimes when we draw vectors, we use an arrow to represent them. That's why I kind of drew that arrow for the 30 degrees. So when we draw an arrow to represent a vector, we don't just draw it any old way. Let's say we wanted to draw 10 newtons to the left. Okay, let's say maybe this is my XY grid. 10 newtons to the left may look something like this. Okay, 10 newtons to the left. My arrow points in the direction of my direction. That should be kind of obvious, right? If I'm drawing a vector to the left and it's an arrow, it's going to be pointing to the left. And also, my magnitude is going to be represented by the length of my vector. So if this vector here is 10 newtons, okay, if I want to draw a vector that is 5 newtons, I'm going to draw an arrow that is half the length of this vector. So that would be 5 newtons to the left. If I wanted to draw 20, I would have to double the length of my 10 newton vector. Okay? So the magnitude is represented by the length of the arrow for a vector, and the direction for a vector is represented in the direction of the arrow. All right, so hopefully we have a decent idea of scalars and vectors, because now we're going to start talking about some types of scalars and vectors. We have a few key terms to talk about. The first one is position. Okay? And we define position as the separation between an object and the origin. So again, if we have some, if we're working in 2 dimensions and we have some XY grid, then our position is going to be a vector pointing from the origin of our coordinates to wherever our object is located. So the position of this little blue dot is going to be represented by some vector that looks like this, okay? If we're working in 1 dimension and we're just working on a kind of like a number line here, and the blue dot is, let's say, over here, and we say the origin is right here in the middle, then our vector is going to look something like this, pointing from the origin to the position. Okay? So position is a vector. That's important to remember. Okay? Position is a vector. All right, but the position just really talks about where an object is at one instance in time. Well, if we want to talk about the path an object takes or how an object travels, then we can't just take a look at where an object is at one time. We have to consider how the object moves over a course of time or over an interval of time. And we have 2 ways of describing that motion, 2 different terms. We have distance and we have displacement. Okay? And they may sound kind of interchangeable, but they are a little bit different. We define distance as the length of the path that an object travels. The length of the path that an object travels. Okay, I'm going to make that a little smaller. It's a little large. So that is how we define distance. All right, and let's say this blue guy, he started at the origin, and the path he took to get from the origin to where he is now looked something like this. Okay. All right. Well, the length of this little swirly line would be the distance. All right, it is the length of the path that an object travels. That's how we define distance. And distance is what we consider a scalar. It does not have any direction associated with it. It is just a number. So if the length of this squiggly line is, say, 25 meters, then 25 meters is our distance. It doesn't have any direction. The direction that the object is traveling is actually kind of constantly changing in this instance. Meanwhile, we also have another way to describe motion called displacement. Okay? Whoops. And displacement we can define as a change in position. Displacement is just a change in position. And the difference between displacement and distance is displacement doesn't care about the path traveled. All it cares about is where you start and where you end. It's just about your change. So this red arrow also, besides representing our position, represents our displacement. It represents where the object started at the origin and represents where the object finished at the displacement. Or let's say we have some green guy who started here. Let's say this was the starting location of our green guy, and our green guy ends here. Okay? Our displacement would be some arrow from the start to the finish. Even if the path of the green guy looked a little curvy like this, this red arrow represents our displacement. It's just our change in position. And we represent displacement with the symbol delta x. Why delta x? Well, delta means change. This delta, this triangle, is the Greek letter for change, okay? Or the Greek symbol that we use to represent change in math. And x is how we define or how we describe position. X is our variable for position, at least in the horizontal axis, okay? So position, we're going to be using x for a while. We're going to use x to represent position. So change in position is going to be delta x. Don't get confused here. This is all one variable. Delta and x are not separate variables. Delta x is one variable. It means change in position, okay? And for our class, we're going to use d for distance, but we'll see if that changes. Many other classes use different letters for distance, or distance is just written out. I intend to stick with d. If that gets confusing with some other variables, then we can go ahead and change it, but for now, d is distance, okay? So d is distance, x is position, and delta x is displacement, and displacement is a vector. All right. Displacement is a vector. And delta x, or displacement, we can write in another way as our final position minus our initial position. So basically, where we end minus where we start. Those little subscripts, f and I, are just for final and initial. So let's say on the number line, we have a green guy that starts right over here, and the green guy ends all the way here at the end, okay? And let's say this is a position of 1, and this is a position of 5, okay? X equals 5. Well, our displacement here is going to be our final position minus our initial position. So using our formula here, our displacement is our final position, which is 5, x final equals 5, minus our initial position, and our initial position is 1. So our displacement would be positive 4, or 4 in the positive direction, okay? we can have a negative displacement, and if we take right to be positive, which in general we do, that would mean that negative displacement would be a displacement to the left. Okay? All right, so let's move on to the next thing. So we have the difference here between distance and displacement. Let's take a look at another example between the difference of distance and displacement. Let's say we have this red guy here, okay? This little red stick figure. And let's say that he travels 20 meters to the east here, 20 meters in the positive direction according to our number line, and then another 40 meters in the negative direction and ends here. What is our distance and what is our displacement? Let's start with distance. See if you can figure out what our distance is. Okay, pause the video. And if you said our distance was 60 meters, you would be correct. Our distance is the length of our path traveled, and we know our guy started moving toward the right for 20 meters, and then doubled back another 40 to negative 20, okay? So 20 to the right, then 40 to the left. That ends up being a total distance of 60 meters. Meanwhile, what is our displacement? Is it going to be the same? Or is it going to be a little different? Pause the video, see if you can figure it out. And if you said our displacement was negative 20 meters, you would be correct. Remember, it's got to be negative. Why? Well, our displacement is our final position minus our initial position. X final minus X initial. And our final position, where we ended up, was at negative 20 on the number line. So negative 20 is our final position. And our initial position is just the origin, 0. So negative 20 minus 0 gives us just negative 20. And that is our displacement. But wait, we said that displacement was a vector, didn't we? Where's our direction associated with this? Well, for now, since we're just working in one dimension, our sign is actually going to be our direction. Negative is going to mean to the left, and positive is going to mean to the right. So as long as we're working in one dimension, we can just say positive or negative is our direction. Once we start getting into two-dimensional space, we're actually going to have to be a little more specific with our direction, but for now this works, okay? All right, and I also have this graph over here, and I want to see if we can take a look at this position versus time graph and describe the motion of the red guy using this position versus time graph. So now he's going to follow another path of motion. He's going to follow the path of motion of the graph. And I want to see if you guys can figure out what this motion is going to look like based on this graph, okay? So take a second, see if you can figure out, based on this graph, how this person is moving. All right, now that you've paused the video, let's take a look. So one of our temptations when looking at one of these graphs is to say, oh, the red guy just travels the path of the graph. So he's going to start here, and then he's going to go up and to the right. Then he's going to keep going right, and then he's going to go down into the right. But that's not actually true. If you notice, our x-axis is time. So this is just how our red guy is moving over time. So let's take a look at 0 seconds. At time 0 seconds, where is our little red guy? Well, he's at a position of 20 meters. This is his starting position, okay? Over here at 20. Time equals 0, he's over at 20. And then 1 second later, he's still at 20 meters. He didn't move at all, right? That first second, he did not move whatsoever. He just chilled there. And then, over the course of the next 2 seconds, he really flies, all right? This is some superhuman abilities stuff. He travels over to 60 meters over the next 2 seconds. So he chills at 20 for a second, and then over the course of 2 seconds, he zooms over to 60 meters. And then for another second and a half, from 3 seconds to 4.5 seconds, he just chills at 60 meters. You see how his position according to this graph is still 60? Anytime we have a flat line in a position versus time graph, we know that our object is not moving. And then from 4.5 seconds to 6 seconds, he wheels it back over to a position of 20 meters, okay? So the first segment of this graph is him chilling at 20. The second segment of the graph is this guy zooming over here in 2 seconds. The next segment is chilling here for 1.5 seconds. And then the final segment of the graph is him zooming back over to 20 in 1.5 seconds. Okay? So that's how we read a position versus time graph. All right, now we got to talk about some more key terms. We got to talk about time, speed, and velocity. Now, I know you're thinking that speed and velocity are the same thing, and that's because in everyday language, we do define them as the same thing. We say speed and velocity interchangeably, but in physics, we're going to have different definitions for these two guys, so we got to be careful with that. But first, let's start with time. A time interval, we use the letter t to represent time, or sometimes just delta t. A time interval is just some interval of time. It's some period in time. It can be as short as a split second, or it can be as long as infinity, right? But when we talk about intervals of time in physics, and especially kinematics, usually it's going to be measurable on the scale of seconds. We're going to be talking about a few seconds, half a second, 500 seconds, whatever. Just typically some reasonable number, but we might have some extreme examples. And we see that delta again. Delta means change, right? So we could say that delta t is just a change in time, or our final time minus our initial time. Okay. Now, the reason that we use t and delta t interchangeably and we don't use x and delta x interchangeably is because delta x and x mean two different things, and they're both interesting for us to look at. Delta x means displacement, while x just means a position at an instant in time, right? So those are two different pieces of information. Meanwhile, for time intervals, we can use t to represent time interval because when we're describing the motion of an object, it has to be over some period of time, right? An object can't move if time isn't moving. So in order for us to describe the motion of an object, we have to be talking about a time interval. We may refer to specific times. We could say, once we start our stopwatch, theoretically, oh, at a time of 2 seconds, where was this object? Or at a time of 4 seconds, where was this object, right? If we think back to our graph, we could identify where it was at 2 or 4 seconds, where the red guy was. But typically, when we're doing problems, we're going to be using t to mean an interval of time. So, oh, this runner ran to the right for 5 seconds, or this runner ran to the left for 10 seconds. So t can mean an instant in time or an interval in time, okay? Delta t will always mean an interval in time. All right, now let's talk about average speed and average velocity. So the difference between average speed and average velocity is a little bit subtle. They're both a rate, okay? And what I mean by a rate is division is involved. They're both measured in a unit of meters per second, okay? And the difference between a speed and a velocity is that speed is a scalar. Also, by the way, time is a scalar too. In physics, we measure time in seconds. So time is also a scalar. Speed and average speed is a scalar. Meanwhile, average velocity is a vector. So that means that speed does not have an direction associated with it. Meanwhile, velocity does. And their definitions are also slightly different. We say that speed, I'm going to use a little s for speed in this class, is equal to distance over time, okay? Distance over time. Meanwhile, average velocity, or velocity in general, is just displacement over time. So I'm going to use delta x for displacement. and delta t for our time interval. Okay? Average velocity, and if we want to represent an average, we put a little bar over the term. So v is velocity, and if we put a little bar over it, that's average. Average velocity is displacement over time. So the direction of our velocity is just going to be the direction of our displacement. Okay, we're just going to steal that direction associated with our displacement and use it for our velocity. Okay, so let's take a look at the difference between average speed and average velocity. So we have this guy here, right? And we said that according to this graph, I'm going to blow this graph back up. From 0 to 1 seconds, red guy chills at 20, actually, just chilling here. And then for a couple seconds, runs to the right by 40 meters, chills there for a second and a half, runs back to the left by 40 meters. So let's talk about a certain time interval. Let's pick the time interval that we're interested in, okay? Let's say we're looking at a time interval that starts at a time of 1 second, and let's say it ends at a time of 6 seconds. We're just interested in 1 to 6 seconds. So our time interval here is going to be a total of, well, our final time is 6, our initial time is 1, so our time interval here is 5 seconds, okay? And we want to know the average speed of our little dude and the average velocity of our little dude over this time interval. So let's start with the speed. What is the total distance traveled? Well, we go 40 meters to the left, or to the right, apologies, and then another 40 meters back to the left after a second and a half pause. So our distance traveled, our path length is, take a moment, pause, what do you think it is? It's 80. It's 40 to the right, 40 back to the left, okay? So our distance is equal to 80. And so if we want to calculate our speed, we know that speed is just our distance over our time interval, distance over time. And so I would just take 80, put it in the top for the distance, and 5, put it in the bottom for the time, and I would get a speed of 80 divided by 5 is 16 meters per second. Okay, and that's it. Make sure to include your unit. We said that we're working on a scale of meters and seconds. So in case you're wondering where I got that from, that's over here on the axes to the graph, meters and seconds. All right, so that's our speed, but what about our displacement, or our average velocity? Our average velocity is equal to our displacement over time, so we need to decide what our displacement is, okay? What is our displacement? Take a moment, pause. And our displacement is actually surprisingly 0. What was our final position? We ended at a position of 20 meters. And our initial position was also 20 meters. We started and ended at 20. So 20 minus 20 is equal to 0. That is our displacement. And so what's our average velocity going to be? Well, if we divide 0 by anything, we will find that it still ends up being 0. And so our velocity is 0 meters per second. And here's our one exception where we're not going to have a direction, is when our vector is 0, because you can't have 0 in a certain direction, right? All right, so that is our difference between speed and velocity. Let's talk for a minute about instantaneous velocity, though, because we're able to find, oh, apologies, I should mention, there's another way you can find velocity on a graph. Can you tell what it is by any chance? Think about what the velocity is from time of 2 seconds to a time of 3 seconds. See if you can calculate it and see if you can relate it to anything on the graph. For a second. And if you notice, our average velocity over this interval is our change in position, which is 20 meters, over our time interval, which is 1 second. We get 20 meters per second. All right, positive 20 meters per second, that's our direction. And what is the slope of this graph? Oh, would you look at that? It's 20. The slope during this interval is 20, okay? And so the slope of our position versus time graph is actually going to be our velocity, all right? Our velocity over this interval is also going to be the slope of this line. And we see that we have a rise of, well, it's actually a negative rise of negative 40, right? We're dropping, and a run of 1.5 second and a half. And that's going to give us, I believe, 26 and 2/3, negative 26 and 2/3, 0.6 repeating, okay? Meters per second. So if we have a negative slope, we're going to have a negative velocity. If we have a positive slope, we're going to have a positive velocity. And if we have a zero slope, we're going to have zero velocity. Our object is not moving. And that's a really useful tool for finding the velocity over an interval using a graph, because then we can do it visually and a little bit more easily. Now let's talk about instantaneous velocity, which is just a little bit different from average velocity, okay? Instantaneous velocity is just our velocity at an instant. So if we want to find what is our instant velocity at time equals 2 seconds, what's our velocity here? Then all we have to do is find the slope of the line that that point is on. And we know from last time that the slope of the line that this is on was 40. So we know our instantaneous velocity, or just v, is 40 meters, or apologies, 20 meters per second, okay? Our instantaneous velocity at 4 seconds is going to be 0 meters per second, all right? Now, what if we had a position versus time graph that looked like this? How would we find the instantaneous velocity then? Because the slope of this line is constantly changing. What would we do? Got any ideas? Pause the video, think about it. All right. And if you know what a tangent is, you may have thought about a tangent line. A tangent is basically the slope when we make our interval smaller and smaller up into a certain point. So it's almost like our instant slope for a curve. And our tangent of the curve in a position versus time graph is actually going to give us our instantaneous velocity at that point, okay? All right, so let's move on now. Now, one skill we're going to need to be able to do is sketch a velocity versus time graph based off of a position versus time graph. And over here to the left, we have a position versus time graph from earlier. We want to sketch our velocity versus time graph. So what we're going to do is we're going to do it very methodically. We're going to break up our position versus time graph into different intervals. Anytime the slope is changing, we're going to mark that as a new interval. So we're going to start over here at the left. I'm going to do this in red. Start over here at the left and go until our slope changes. And our slope changes here at 1 second. So we're going to break it up there and then keep going. And our slope changes again at 3 seconds and again at 4.5 seconds, and then it ends at 6 seconds, okay? So these give us our intervals. We need to find the velocity over interval 1. I'm going to mark that in red. Interval 2, which I'm going to mark in blue. Interval 3, I'm going to leave that in green. And then interval 4, I'm going to mark that in yellow, okay? All right, let's see if we can sketch our velocity versus time graph for these intervals. So our first interval, we need to decide what our velocity is from time equals 0 seconds to time equals 1 second. The first second. Well, what's our slope? Because our velocity is just the slope of our position versus time graph. So if we look at this, we know our slope is just 0. So we know that our velocity is just 0. So we can just draw a line that stretches over the course of 1 second at 0 meters per second, because that's our velocity there. Okay, let's next do from time equals 1 to time equals 3 seconds. What's our velocity now? Well, if you remember, our slope for this line is 20. So we can go ahead and put a line at 20 meters per second, positive 20 meters per second, until time equals 3 seconds. All right, next, for 1.5 seconds until from 3 seconds to 4.5 seconds, we have another flat line, which means a slope of 0. So we're going to draw our third interval just like that. Then finally, our last interval has a slope of, if we remember the calculations from last time, this was negative 26.6 repeating meters per second. So this is going to be a little ugly. I'm actually going to use black for this one. I don't have black, it's an option. All right, it's going to be an ugly yellow line. But for 1.5 seconds, I'm going to draw a line roughly at negative 26.6. So about here. Yeah, that, you can't see that. I'm going to draw that in red. This is what it's going to look like. All right, I'm going to make this interval red again. Boop. All right, so that's roughly where negative 26.6 meters per second is. We don't have to be super precise on it, but not quite halfway between negative 20 and negative 40. Okay, so that is our velocity versus time graph. All right, now we've been working with constant velocity a lot, and that's all we're going to be doing for today's video. Before we finish up, I want to do a problem involving a constant velocity, and for that we need an equation, and I'm going to derive an equation from a definition that we already know. We already know that average velocity is equal to displacement over time. So I'm just going to rearrange this real quick by multiplying both sides of the equation with our time interval. Okay, I'm going to multiply both sides of the equation by delta t, and I'm going to end up with an equation that looks like this. Delta x is equal to average velocity times time. And I'm just going to write it the way we usually see it. Delta x, is equal to average velocity times time. And if our velocity is constant, then our average velocity is just whatever constant velocity we have, because it's not changing, okay? So now, let's see if we can solve a problem using this. I have a problem here. A cross-country runner can run at an average, that's supposed to say speed, oh man, I made a lot of typos, speed of 5 meters per second. A cross-country runner can run at an average speed of 5 meters per second. How long will it take them to run a 5K? Well, what pieces of information did it give us? Let's write that down first. Do we know the displacement of this cross-country runner? We're going to go left to right for the variables. Displacement, do we know it? Yeah. We're asked about a 5K race, and I happen to know that a 5K is 5,000 meters, okay? 5K is 5,000 meters, so our displacement here is 5,000 meters. That's why it's called a 5K. Then, we also know the average speed. The average speed of this runner is 5 meters per second. Okay, 5.0 meters per second. We want to know how long it would take them. So we are solving for t. How much time is it going to take this runner to run this 5K? Let's find out. So what we're going to do is we're going to plug our values into this equation that we have. So delta x, we're going to replace with 5,000 meters, okay? It's equal to average velocity, which we're going to use 5 meters per second for, times time. And since I don't know time and I'm solving for time, I'm just going to leave t as my variable. And now I'm going to just use algebra to solve for t. This is why we did the whole solving for variables thing. So I have 5,000 meters on the left, 5 meters on the right. So in order to solve for t, all I have to do is divide 5,000 meters by 5 meters per second. Boop, just like that. All right. Include the meters there. And we get a final answer of 5,000 divided by 5 is 1,000. And what is meters divided by meters per second? Well, if you know about fractions, you know that's going to leave us with a unit of seconds. Okay? We're going to flip that meters per second there. Or you could just know that the unit for time is seconds. All right? Boom, we have 1,000 meters per second, or 1,000 seconds. Apologies, that would be really fast. And that's our final answer, 1,000 seconds, okay? So that's an example of how we use the constant velocity equation to solve a problem. And we're gonna see this a lot in physics, where we have some equation and we have all the values in that equation except for one. So we just plug in all those values and leave that one that we're looking for as just a variable and solve for that variable. Okay, all right. But what happens if our velocity is not constant? Well, what happens is we're gonna find out next time in the next video, because today we're just worrying about constant velocity. So when we talk about changes in velocity, that's gonna be the next video, all right? So I hope you all have a wonderful rest of the day, and best of luck with whatever physics you're doing. Study hard, take care.